So I'm David Blevins, and I work in a company, Tomitribe, and we do a lot of stuff around middleware. So a couple years ago, we were one of the creators of Apache Tommy, and we do a lot of support for that stuff. And a couple years ago, a customer asked us, hey, we rolled this stuff out, now what? What are we going to do to secure this stuff? And we're like, okay, well, basic auth. Of course, that's not going to fly. And so we did a lot of research and to try and figure out how to get up to speed, and it was kind of an interesting story. Having participated in the standards for a really long time, I don't just read the specs because I know there's like usually story behind the standards. So one of the things I did to try and get up to speed was look at the names of the people who were on the spec at the beginning, and look at the names who are on there now, see who left, contact them, say, what do you think about the spec? Why do you leave? And they can't wait to rant. And so you learn a lot of stuff really quickly, but one of the things that I really had a problem with trying to choke down this whole world was how completely complicated it is, almost like it's intentionally designed to deceive you, because there's so many choices in specs. And I think this quote really summarizes the problem of security these days, which is the nice thing about standards is there are so many to choose from. And so kind of after going through this process of learning, I really wanted to put together a talk to try and bring a simple perspective of it, because I think that you really don't find simplistic talks about security. For some reason, you either get people who are really into the details and can't really describe it at a high level, or people who are too afraid to talk about it. So I decided I wouldn't be too afraid to talk about it, and I should come out and describe it anyway. So, one of the things that's tricky in standards is, well, they're always like, no matter what the topic is, like 200 pages or 100 pages, even though maybe there's not much there. We always rename everything that already existed. So, I guess if you're paid to write a spec, you're paid by the page apparently. And so, it's an interesting thing. Another thing that's kind of tricky with standards is security related specifically is everyone you read, you feel like you know less, because it mentions some other spec that's an extension or an addition or relates to that one. So you go reading that one, you go, when am I going to go to the end? When am I going to be finished? And so So in this talk, we're basically going to try to show, how REST security is done at a high level in the most common practices architecturally, and what that means in terms of how you roll out a system. So we are going to show actual HTTP messages and things like that, but really we're going to start with an architectural perspective. So we're going to cover kind of 3 styles of security that are out there. Of course, we're going to do a recap to show kind of like a baseline what our security looks like with with basic auth as a baseline. We're going to morph that into OAuth 2 using regular tokens. See how that looks with JSON Web Tokens and what that does to our architecture. And then we're going to kind of go into an interesting style of security that's new called HTTP signatures, which is, I like to describe it as the Amazon style. So we actually got that recommendation from them. The client library for EC2, all the AWS clients are written in Java, even the command line one. And so we went and found the source code and said what they were doing for security. They use a concept called signing, message signing. And we asked them, hey, can we use it? And they're like, well, there's actually a much simpler draft out there, so we're going to go into that. And there's actually kind of some compelling reasons to use them both. So before we get into it, so who's using security now? So who's basic auth, right? Let's do this. Let's go basic auth. And it's OK. All right, so we got a couple hands. Who's using OAuth? All right, that's pretty good. For those of you using OAuth, who's using OAuth with JSON Web Tokens? Fewer hands, so that's good. I mean, not good, but I mean, you're here, so that's good. And then, so we didn't quite get all the hands yet, so some other form of Corba security, I don't know, who has no users? Okay. And then I guess, who doesn't secure your apps? So some of you didn't raise your hand, so I guess, what would be someone list out something that wasn't mentioned? Okay, well. You are using signatures. Do you work for Amazon? Okay, that's awesome. Okay, so in our baseline architecture, so we can actually compare these things and how they actually behave in terms of amount of traffic. We're going to have a baseline type of architecture. We're going to have 1,000 users generating 3 TPS each. They're extremely aggressive users. And so we're going to assume that we have a microservice architecture in the background. All right, and so we're going to say it takes 4 hops to satisfy the call before the answer can get back to the user. So we're going to have effectively 3,000 TPS in total flying at the front door, and on the back side, that's going to result in 12,000 TPS. So that's our baseline architecture. This is with no security. That's just plain up straight traffic. Okay, and so if we take a look at what basic auth looks like in that, and so here's just a quick recap of basic auth. It's extremely secure because we have fancy username and password concatenated together using an extremely complicated algorithm called base64, which nobody knows about, only the highest quality programmers. And so, of course, we're passing everything, username and password every request, but that's not the worst of it. Architecturally, if you want to do a check at the beginning of every request, now we're having basically 3,000 TPS happening against our LDAP server or wherever storing those username and passwords. We have that amount of traffic. So it comes in, and for everyone, we have another 3,000, another request going down. So effectively have 3,000 TPS going against LDAP. Typically, people are not using authentication in the back. Who secures traffic once it enters your enterprise? Okay, 3 hands. That's the common case. It shouldn't be, because of course no one's ever heard of contractors. We don't let anybody in our corporate headquarters that we don't possibly know. In fact, Target. Is anybody here from Target? Good. Okay. So Target. One of the issues that got them severely hacked was, of course, people who were contractors. It wasn't the front door. It was people who they let in, the front door of the actual headquarters, not the front door of the internet. And so you have to actually secure the traffic on the back end, which is kind of one of the things that we should all start moving towards. So theoretically, if you do that and you try to lock things down with username and password again on the back end of the side, now you have 15,000 transactions per second going against LDAP, which totally does not scale. So what a lot of people do is whitelisting. Who's using whitelisting? That's much more common. Well, one person. Okay. I see a lot of whitelisting. It also has some limitations in the sense that whitelisting is the natural enemy of elasticity. If you have something that fires up a whole bunch of JVMs, they all get brand new IPs, and if you bring them down, bring them back up again, you're just going to be continuously getting new IPs, and so whitelisting just does not work with elasticity. Okay, here's another problem with basic auth, or not securing the backend. If you don't secure the backend, you're writing architectures that basically work like this. Microservice A makes a call over to microservice B and says, hey, get me all of Joe's salary information. And of course, microservice B says, yeah, sure, here it is. No proof, no authentication. Just because you're there, you're trusted, and you give away everything to everybody. And this is not exactly the best way to be designing applications. but is unfortunately what we're doing with these days. So basic auth and its lack of scalability and its lack of security is affecting our architectures in many awful, terrible ways. So of course, now we have a hack comes in, and instead of, now let's say we have the evil people from the awesome country Latveria, which is a very real country if you live in the Marvel universe. They come and decide to hack you on the front door, and now they're generating 6,000 TPS in bad hacking traffic. So now we have 9,000 TPS in addition, going against our LDAP system. And so this is just really, really bad. So OAuth 2 is what is being sold as the solution to basic auth and passwords. So the theory behind it is effectively that what we're going to do is give each mobile device a token. And on that mobile, so if you've got one user and they have 3 devices, effectively there's 3 sets of credentials. So you would log in with your username and password, you would get back a token, and each device will have its own token, its own username and password. And the theoretical advantage of this is that if someone loses a device, you can remove the username and password, effectively the token for that device. And if that's great, you can do that for all the ones that people lose. And overall, they don't lose access to all their stuff, just the one that was lost. That's some of the theory that drives OAuth 2 into existence. There's a process of granting and getting those tokens. They call that a grant process. It's very, very fancy. What you do is you post your username and password to an endpoint where you get back a token. See that on the bottom? An access token and a refresh token. They have an expiration on them, and when they wear out, you've got to re-up both tokens. So, so far, we're doing some incredibly new inventions because never before have you used form URL encoded to send a username and password in a post body to a server to get back a security token. I mean, this is basically the same thing we've been doing for the last 15 years, but now this is, but trust me, this is all new, because if I'm writing the specs, I gotta make my paycheck, so I have to rename everything to make it sound like I've invented something. Ever notice, if you've been in the industry for a long time, 90% of what's being portrayed as new is the same, and 10% is actually new, but they've renamed the previous 90%. It's pretty much what's going on here. So once you get that access token, so you send it in your request via the header authorization, and instead of using basic as the scheme, you use bearer. And you take that same access token and you send it over and over and over again till, bam, it eventually wears out. And then now you have to do something called a refresh, which is you take that second token that you were given, and then you post it to the server, and you get back a new access token, refresh token pair. So this is what OAuth is at its core. This is the basic thing. So in this refresh process, we've exchanged our old access token refresh token for a new access token refresh token. So effectively, you want to think of them as one is a fast lane traffic token. You send it all the time until it wears out. You use the refresh token to get another access token refresh token pair. Once you have that new token, you can go ahead and send it just like you were the other one, and then that's how the basic concept of OAuth 2 works. So what have we achieved? We have a lot more passwords. Because those access tokens, if you see them on the wire and you take them, effectively you can be that person. And so this is the kind of funny thing about these kind of standards, in the sense that if you were to imagine bringing a vendor in and you were telling them, we have this password-based system, And we really want to get rid of that and move away from that. And the vendor says, I got the greatest solution for you. It's called tokens. What are tokens? They're strings. What are these strings? They're unique strings that you use to log in. So like a password. No, I don't think you're listening to me. They're called access tokens. And it's sort of like, okay, you know, but if they come in straight in and say, oh, we're going to sell you the solution for passwords is a lot more passwords, of course, you'd kick them straight out the door. So it's sort of like this weird thing where we can't just call a spade, and it's quite ironic. So, you know, another funny thing is grant. OAuth 2 spec calls the whole process of logging in the grant process, and to describe a couple different ways you can get a grant. But of course, it's just logging in. And in fact, they haven't even changed the way the HTTP message looks when you post your credentials there to log in. There is an additional credential called grant type that's usually set to password. But other than that, your form URL login on your website looks pretty much the same way it does in OAuth 2. But of course, it's not called logging in, it's called grants, right? Because, you know, if I'm writing a spec, you know, I get paid by the page. And so therefore, I have to make a whole lot of description. I mean, you could be, like, by the time you even get through the grant section of the OAuth 2 spec, you're like 30 pages in. And they never call it logging in. They call it exchanging credentials for tokens and blah, blah, blah. It's quite maddening. What would be a better word for token? I don't know. Slightly less crappy password. If we were to be honest about it, right? It's very stealable. Or I like to call it an equally crappy HTTP session ID. Because basically, that's what we achieved, right? So we posted our username and password, and we got back a token, which is a string about yay long that identifies us in a system. So how is that different than an HTTP session? Well, if you ask the security expert who wrote the spec, I don't think you're listening to me. I said it's not called the session ID, it's called a token. And you know, it's like, okay. So we've so far just been sold HTTP session IDs with form URL login. Absolutely no different. So this is the way most OAuth 2 implementations have been written for the first 5 years of the OAuth 2 spec. And so what happens with this architecture is that now instead of having 3,000 transactions per second go against OAuth, we're first logging in, we're posting our username and password to the top, so I've moved the LDAP server to the top. Let's say that everybody has to log in with a username and password at a form once daily, okay? So that's 1,000 transactions that are happening over SSL to the LDAP server just as before. Now we're issuing these tokens, we're putting them in a store which is now at the bottom, and now we're doing 3,000 TPS against that. So architecturally, we've gone from 3,000 TPS against an LDAP server to 3,000 TPS against our token server. Did we really gain anything? Or did we just add more points of failure? It's sort of a lateral move from that perspective. Also, if you have a system where you're trying to pass security credentials in the back, let's evaluate how OAuth 2 with just these short access tokens looks when we're trying to lock down our backend. So we'll have one service, call over to service B over there, and give the little access token and say, hey, can you give me Joe's salary information? Another service says, who the heck is this? They say, I have no idea who that is. So of course, you got to make a trip to the token server again. So now we're doing our 12,000 transactions per second against the token server to figure out who's on the other side of these little tokens. And of course, now our token server promptly starts on fire because it's processing basically 55% of all the transactions in the entire enterprise, becoming a huge bottleneck of point of failure. And then it promptly dies, and now we're getting no transactions per second. So effectively, we've taken, exchanged one type of bottleneck for another. That is an HTTP session ID server, no doubt about it. So these access tokens effectively being pointers to state in the back end, maybe we can think of some better names for access tokens. How about access pointer or access primary key might be more on the nose and more honest for what they actually do. But of course, we're not going to call them that because then people might not like them, so we keep them called tokens, which, by the way, token is just some random word for string. And they could have used string, but no, token sounds way more official. So I have a very low tolerance. Another word for OAuth 2 might be high-frequency password exchange algorithm. That's my preferred favorite. I think that much more accurately describes the whole system. We haven't achieved much other than exchanging a lot more passwords a lot more frequently. Because if you see any of these things on the wire, you can pick them up and you can gain access to those systems. So they're just as vulnerable as a password. The only hope is that you exchange them more quickly. But the problem with standards is everything's optional. So after you've read the 100-page of the OAuth 2 spec, you realize refresh tokens are totally optional. And the policy around them is totally optional. So whether they're supported or not is not even a guarantee. And so if there is no refresh token process, then effectively your access token lasts as long as a password because you have no way to get another one other than for the user to log in again. And so we're stepping further back from progress, and it's not great. Enter JSON Web Tokens. So JSON Web Tokens are a way, of course, the greatest thing about the JSON Web Token spec is that they like to think that they're way bigger than OAuth and can solve world hunger. And so when you read that spec, they're not going to talk too significantly about OAuth, and they're really going to talk to you about the very big problems that they solve in the world. But meanwhile, from where we're sitting, we just need to solve this problem of that access token being pretty much crap. And so JSON Web Tokens are a concept where you're effectively taking a JSON map of user data, you're base64 encoding it, you're signing it with a public or private key or a symmetric key, and then you're giving that to the user instead of that short little access token. So inside that thing, there's expiration times, there's information about the user, and all sorts of great stuff. So what we had previously was effectively this as our access token. And when you use a JSON Web Token instead of that, you end up with a much bigger looking token. Now, that looks awful, but bear with me for a moment. We've actually achieved some amazing things just with that short change. Okay, so effectively, what that token is three parts. The first part is what's called a header. The second part is the actual data. And the third part is the signature, or more like this. And here is the slide that tells you what it actually looks like. So we have effectively two JSON maps and the digital signature. So the first JSON map describes how we effectively signed and encoded the middle part. And the middle part is the magical thing that describes the user. The easy way to describe this, that's a cookie. And effectively, I'd like to describe it as a signed cookie. And so here we say, oh, the username is Snoopy. We can have other information about Snoopy. We can have scopes, which effectively can define what permissions or roles Snoopy has. And then, of course, there's expiration and what time the token was issued. And that helps us to get a much more controlled description of when these things expire and how long they should live. And then the bottom part is going to be the actual base64 encoded bytes of the first two. So effectively, what we do is to make the blue part, we take the purple part and the yellow part, and we digitally sign that. Then we encode the bytes, and we make that the blue part at the end. We tack all three of those together, we send that back to the user. So there's a very subtle change. That's why I like to show the architecture, because if you just show this versus the other one, you're going to go, well, I would probably want the shorter one. But there's a very huge impact to just that, okay? So what we had was effectively this. We were posting our username and password to our LDAP system. We were scooping out user information. We were generating an access token, which is effectively a pointer. We're inserting that token plus user information into now our token store. This was the previous way. And then we pass our pointer back. And then the client holds a pointer, and the server side holds the state. That's what we had. What we can do now with the JSON Web Token is effectively subtly different. We first do the same login process. We check their information against our LDAP store or whatever identity store is. We do a scoop of information about that user. We format that as a JSON map. We sign that JSON map. We insert a pointer into a DB for revocation purposes only. And then we send that full map back to the user, and the user is now holding their state. And so now we've flipped it around. Instead of the state being on the server side and the pointer being on the client side, we now have a pointer on the server side and the state on the client side. So what that means is if you have 6 million mobile users, each one of them is holding their own information on their phone, and they send it every request. And you do not have to have 6 million records of state in the back end describing each user in detail. Very subtle but high impactful change. It's a difference between an HTTP session ID and an HTTP cookie. It's very, very significant. So now let's take a look at how this plays out in terms of architecture. If everybody has their tokens on their mobile device, so we have the same login process, or excuse me, I'm sorry, I'm not doing it justice, grant process. I'm definitely not going to get a job as a spec author for OAuth 2 or anything like that anytime soon. We're doing our login process, and we're posting our username and password, and then we're getting back our same access token, except now it's much bigger than before. And the refresh token is going to be very similar. It's going to be this also, if your system supports refresh tokens, which I advise you to ask that question. If you have an OAuth 2 system that you're using now and they don't support refresh tokens, you should ask them what, if they do or not. Some systems that I've seen use the same refresh token over and over and over again. The stronger policy is that they should be single use. You use the refresh token, you get a new access token, refresh token pair. The old one can't be used anymore. That's the stronger policy. Because that refresh token, effectively, if it's not ever expired, you could just log in a whole bunch of times with that, and if someone steals it, it's almost worse than password. OK, so we get now our much bigger access token back. So now instead of sending that smaller one, we're sending our JWT or our JOT, and we send that every request. And now here's where the impacts are more visible. So just as before, we're going to say we're logging in with username and password once a day. So our 1,000 users are going to trigger 1,000 requests per day to our LDAP system. Then they're all going to get back access tokens, which are JSON Web Tokens that has their information in there. It is the most sane thing for them to be public-private key signed. I'll go into that later, but some gateways just do symmetric signatures. There is a subtle difference as well there. But effectively, what we're going to have is 3,000 tokens per second being sent, because we have 3,000 transactions per second being sent. Each of them is going to have an access token in it, a JOT. And we're effectively able to check those using either the symmetric key that was used to sign the token in the first place or the public key corresponding to the private key, right? So who's familiar with just basic encryption in terms of symmetric versus asymmetric? Okay, excellent. There was some hands that didn't go up, and so effectively, the difference between a hash is a signature is best described as a hash that's encrypted. I mean, that's a cheap way of saying it, and some people will get up in arms and saying that's an oversimplification of the process. But hashing is effectively the act of taking a number and you mutate it as you see the data go by. So effectively, imagine you have a stream of data, you stream a file through, and you got a snow globe, and you just shake it up, and you keep shaking, and when the data stops moving, you stop shaking, and whatever that number is, that's the hash. And it's statistically unique. And so if you change 1 byte, theoretically, the hash should come out differently. And then so to protect that with identity, you're adding some sort of encryption so that you can prove that whoever's made that hash is the one who's authorized to do so. So we're able to check that JSON Web Token using the public key that's there on the gateway. So with a simple signature check, we can verify that token to be valid or invalid. We don't have to do any hits on a persistent store. And so effectively, instead of having the 3,000 TPS against our stateful OAuth 2 token store, we now have to do a check basically once per refresh. And that's a policy that's common. We have a system that does this. We check a store on the refresh to see if we should allow that user to get another access token refresh token pair for the purposes of maybe they lost their device, maybe their computer was hacked, and so we go find their tokens and we in the refresh tokens that are stored, and we wipe them out. And so effectively, if you only check your store for identity, for a revocation, in the event, which is rare, that you need to actually aggressively lock a user out, if you do that like once an hour, then effectively you wind up with 0.55 TPS going against that refresh token store. The excellent thing about this is if you have this public-private key scenario set up, the gateway holds the private key and is the only one that can basically create tokens. You give the public key to all the services in the back end, and they can also verify tokens. The value of that is that you can start to propagate identity from front to back in a very cheap and effective manner. So we're going to add in signature checking, JWT checking in the back end, and we're not adding any hops to that middle server there in the bottom. So we're not going to have the 15,000 TPS going against the center store, and we're going to get security in the back end for the cost of 0.55 TPS. It's a very significant change. And so now we have a world where effectively, when that microservice says to this microservice, can I have Joe's payment information, unless this microservice here passes the JWT token of Joe over to that microservice should say, no way, you're not going to get Joe's payment information unless you have Joe's access token. So the right way would be for that access token to be passed from microservice to microservice, which means you and your app code are taking it from the incoming HTTP message and you're putting it into your outgoing HTTP messages to your other microservices. And that's how it propagates through the enterprise. And provided you take the public key of the gateway and you install it or give it to all of the Docker images and put it all in the images of all your various microservices, they can check that access token for being forged or not with simply a public key check. They don't need to handle the revocation or any of the fancy stuff because you can just let the gateway do that, but at least no one can forge identity in the back end of the enterprise. And so now, when microservice A says to microservice B, give me all of Joe's salary information and passes Joe's token, microservice B should say, You got it. Here it is. And now we have a very strong way to propagate identity from the front to the back of the enterprise very cheaply without any hops to a center server. So we've achieved effectively stateless REST security. And so, the funny thing is that when we talk about our architectures as developers, we always pat ourselves in the back and go, oh, we wrote a stateless architecture. And then what do you use for security? It's something. And then, well, we go and write these beautiful stateless architectures, and then the security team comes and slaps on a stateful security system and ruins the whole thing. But we don't really think about it because it happens at the end of the project, and so therefore, we still walk around patting ourselves up in the back going, we have a totally stateless architecture. Yeah, except for the fact that you're doing all of your requests are hitting your stateful security system. So there are some benefits to this aside from just the fact that we can propagate state from front to back. Now let's have Latveria come back again and try and hack us one more time. So they're sending 6,000 TPS in invalid tokens at the front door. And normally, if we were doing a stateful system, we would have to go to some token store and check to see if those tokens are valid or not. So that evil country of Latveria is triggering 6,000 TPS to our central point of failure, which is not a good thing. But with a JSON Web Token, we can check those tokens that Latveria is sending to see if we made them by doing a simple signature verification. If the signature doesn't verify, we drop the token on the ground. We don't do anything else after that. So what effectively means is that evil traffic can be stopped at the front door by a simple asymmetric or symmetric signature check that can happen in memory. And the key of the gateway, you're not going to have 1,000 of them. You're going to have one. And so you can hold that thing in memory. You can horizontally scale that extremely easily. And you can effectively block out all that bad traffic with no hits to a store. So effectively, the only time you're ever going to do any refresh check or any checks on a store is for valid traffic. It's for honest traffic. So effectively, honest traffic is not affected by evil traffic. Whereas if you have a stateful security system where those tokens are being checked against the store, evil traffic and good traffic hit the same spot. And evil traffic can affect good traffic. But if you use this simple technique where you're signing those tokens, you can check just in memory really quickly that those tokens are valid or not and stop them cold right at the front gate. So just as before, we were having 3,000 transactions per second going through, straight through the gateway, very little work, and then we have our work on the back end checking those tokens. But that additional 6,000 TPS has absolutely no impact on our back end or on our store, and it's dropped cold at the gate. A great application you can use to try and verify these tokens and use, to make tokens or work with them in your testing code is the Nimbus library. So I would recommend, grabbing a snapshot of that. It's pretty much the most popular one out there for composing the various kinds of JWT tokens. OK, so that describes the OAuth perspective of the world, which is very fantastic for kind of mobile usage, where you have a user on the other side, and they're logging in. You're creating this thing that describes the user. But when we were doing our research, we came across the Amazon approach. And they're doing, a couple $2 billion of business not using OAuth. So it was very curious to us what exactly that's all about. So they use this concept called message signing. So they're taking and employing the same concept of digital signatures. But what they're doing is they're having you sign your actual HTTP message. And so they do it in a very complicated fashion. They sign like 3 different things, and then they sign the signatures, and then it's all really super, crazy layer on top of layer. But what they recommended to us was to go check out this other spec called HTTP Signatures, which is in draft form. It's actually, I don't know how it's going to actually graduate because it's like only 20 pages. So they need to add at least 80 pages to that thing in order for it to finally become an official standard, I think. So it's too simple. It needs to be ruined. And so you read it, and it's dead simple. You can understand it in a day. And I apologize in advance for its lack of sexy technobabble. So effectively, how it works is you have all of your headers and all the stuff there. You make a signing string, which basically means you make a piece of data that you're going to hash and sign. Just like the JWT token is hashed and signed, that map is hashed and signed. Instead of signing that map, which the gateway does, you as the caller, you as the client, you sign your headers. So you take the headers of your outgoing HTTP message, you concatenate them together in a big long line separated by new lines, and then you hash, then you use your symmetric key to sign that. You take the base 64 encoded version of that signature, you put it in the header of the authorization, along with the name of the key you used and the list of headers that you signed. You're allowed to sign any headers that you want. You don't have to sign all the headers if you don't want to. Per recommendation of the HTTP signatures spec, you should sign at least the date header. Can anyone guess why? Replay attacks, exactly. And you cheated because you're doing this already, but I like it anyway. So it's not cheating to know things. So, so effectively, unless you have some part of data that changes, the hash is going to come out the same. And if the hash comes out the same, the signature is going to come out the same. And if you're sending the same signature over and over and over again, then someone can just see that on the wire, pick it up, put it in their message, and send it off and pretend to be you. So you have to have something in the message that changes so that signature won't be valid if someone tries to reuse it. And I'll show you exactly kind of, how signing really is the secret sauce to all of this security. So to show a close-up of it, we simply have these 4 parts that we include in the authorization header: the name of the key, the algorithm, the headers, the signature. So how this would map to like Amazon, for example, is when you create an account with Amazon EC2, you get an access token key ID and an access token. And anytime you use their client library or anything, you have to give those 2 bits of information to the client library. What they're doing with that is they're using the key value to sign the outgoing message. They're putting the key name in the actual message, and they're sending it off. On the receiving side, Amazon is taking the message that they got. They're making the same signing string using the same format and same rules based upon the data they see in the incoming HTTP message. They look up what your key value should be. Then they hash that thing, and they sign it with the key they think you have. And if the bytes come out the same, AKA those base 64 bytes, if they come out the same, you're allowed in. If they don't come out the same, a few things could have happened. 1, you lied. You're not who you say you are. 2, you are who you say you are, but someone tampered with your HTTP message and changed the value of one of your headers or changed the value of the body. And then now your message doesn't verify. Either way, you don't want that. And so Amazon doesn't let you in if any of those things happen. The difference between this and the JWT thing is the signature on a JSON Web Token is around the user data, not around the HTTP message. The signature around an HTTP message signing thing is the message itself. The 2 of them actually fit very well together. I'll go into that in a moment. But there is an issue with this approach in the sense that it's great because there are no secrets sent on the wire, So this is the good part. No secrets sent on the wire. You don't have to use SSL if you don't want to. And effectively, we're sending no secrets of any kind, no passwords, no tokens, nothing that can be simply observed and stolen, right? Because effectively, what you're taking is that your Amazon key never leaves your pocket. You know, it's a nice way to think about it is if you're taking your HTTP message, you're putting it in an envelope, you're putting some wax on there, and you're taking that thing and you're stamping it and you're sending it off. You never send the stamper. You just send a reflection of the stamper. And so there's nothing for people to steal. That signature is only valid for that one message because you're changing data like the date header and so on. And so therefore, there's going to be a new signature on your next message and a new signature on the message after that. And so if they want to hack your account, they're going to have to figure out how to reverse engineer your key from observing many, many signatures. And it's not exactly an easy thing to do. It certainly is a lot harder than just looking at your password or looking at your access token, even if that access token is a JSON web token. If you see it on the wire, you can be that person. And so that's the nice thing about this approach is that nothing that needs to be protected is on the actual wire. If someone observes 100% of that message, they can't be you. It does bring back the problem of there is no way to communicate the user's identity from all the way over here to all the way over there, because if we have 4 hops at each individual part of our back end, we need to sign each of those individual messages separately. Because the call that microservice A makes to B, which makes to C, which makes to D is going to be a different HTTP message. The resulting signature is going to be different. Unless you have the user's key on all those systems, which you wouldn't, then you are effectively only identifying server A to server B, and server B identifies itself to C, and nothing represents the user. So it does put back the issue of one server effectively saying, just because you can talk to me, I should let you have everyone's information. So that's why if you combine OAuth 2 and signatures, you take what are effectively orthogonal concerns and you mix them together to have a best-of-breed architecture. So you still have users log in via OAuth 2 at the gateway, so that you can get a token which can be put in any HTTP message and sent through your backend, okay? But then, to prevent your backend from being a little too open, you still implement signatures from each individual point in the network. And the reason you would do that is because, let's say, the reality is you don't have one team who supplies all your microservices. You have several different teams who supply several different parts of your architecture. Maybe you've got one team that has all the personal identifying information for people who are your users, and they have an endpoint that exposes that information. And if you simply add the policy that anybody who has an access token of the user should get that, you might open yourself up to some vulnerabilities still in your enterprise. Say you've got team B over here, and they're responsible for inventory of stores, but they get that person's token because they're anywhere in a call chain, right? There's an app that does all sorts of things on behalf of the user, and they see the token at some point, and they decide to go over to the personal identifying information endpoint and say, hey, give me all Joe Seller information. They would still get it. Especially if, like I say, especially if that token becomes like a very high value piece of credential and gets sent around through the back end. So what you do instead is you issue a symmetric key that is required to be in possession of the servers who need to call that REST service. So that REST service effectively can only be talked to by other teams in the enterprise who have the corresponding symmetric key. You don't need to make a symmetric key per service, but you can make them per app or whatever kind of domain you want to make and define. You effectively generate and assign a symmetric key to that service. You hand that out to only the people and only the systems who should be allowed to talk to you. You combine that with the OAuth token, and now you have the systems identifying themselves to you, and these systems over here can't talk to you, neither can these systems. And you have a mechanism to identify the user traveling through the enterprise, and effectively we've achieved nirvana of security in our back end, and it's all done in a stateless way, because we can hold these symmetric keys in our Docker image right next to the public key of the token server, and we got two credentials, and we're able to verify everything that comes our way without a trip outside the server. So effectively, signatures is driving all of modern REST security these days. So if we do this, now we have a mechanism where we can still pass that security credentials all the way from the front to the back. And each hop is also identifying itself to the server next to it in terms of saying whether or not it should or shouldn't be able to talk to that server. In the previous way, if we were to do the OAuth 2, we would still have security credentials being sent. So we still have the user logging in. This should not say passwords. It should say tokens. I have to update the slide. So effectively, with this hybrid approach, we're doing heavily OAuth 2 at the front gate, and then we're doing heavily signatures in the back end, still propagating those OAuth 2 tokens. So the observations here are that, at a high level, the commonality between all of these techniques is that digital signing, digital signatures is driving security in the modern day for REST. And if you understand that concept, you can get quite far in simplifying the world. And so, the plain OAuth 2 approach, the best way to think of that is that's an HTTP session ID. Okay? So you have that pointer to the back-end state, but it's effectively a stateful architecture. So OAuth 2 with a JSON Web Token is a signed cookie. It's a stateless architecture. So the fact that they're both called OAuth 2 is almost like painfully misleading, because one is a session ID and one's a cookie. And so, if you, what I would recommend everyone to do is go out and get yourself familiar with the concept of digital signature, because that is really the underlying, secret sauce to all of the stuff going on here. So I hope you enjoyed the presentation. I know all the sessions are going 10 minutes late, so I apologize to the next speaker. I started 10 minutes late, and I think it's going to probably cascade out. But thank you all so much, and I appreciate the time, and I hope you enjoyed the session.